Okay, welcome back everybody. The next section, now that we've gotten some basics with logs and exponential equations, now we're going to really start solving all kinds of different log equations and inequalities using all the stuff that we've learned about so far. So for this section, I'm just going to do a bunch of examples, a bunch of different kinds of questions that you can see. Hopefully that'll help you kind of learn to to recognize when to do what. Okay, so some of these will be very similar to the problems that you did when you were in Algebra 2. Others will probably look a little different, and that's okay. But I think you guys can handle it, so you guys will do a good job. All right, so let's say we have 4 to the x equals 3 to the 2x plus 1. Okay, so far what we've talked about is maybe, first of all, 4 and 3 cannot be made into the same base, so that's not an option. If we switch it to log form, there's actually 2 different bases to pick from. Okay, so I like to say that if that's something that happens, like which base should you use, right? Should you do log base 4, etc., or should you do log base 3? Okay? Instead of worrying about which base to pick, we're going to do something new, which is to actually take the log, and it can really be in any base. Since base 10 is frequently used, you could even do ln if you wanted to, which is base e. I'm going to go with log, just regular old log. I'm going to take the log base 10 of both sides. So log of 4 to the x, that's going to equal log of 2x plus 1. So this is the first step. Take the log of both sides, or if you prefer, you can take the natural log of both sides. Okay, now, one of the reasons that this is a good move in this scenario, oop, I completely messed that up. Hold on one second. Just realized that this should say log of 4 to the x equals log, if we're taking the log of the right side, it's log of 3 to the 2x plus 1. There we go, that looks better. So we've taken the log of the left side, we've taken the log of the right side. One of the nice things about doing this is we have a property from last unit, from last section, that says that anytime there's an exponent in here, you can put that exponent out in front of the log. So I'm going to change this to x log 4, and then I'll do the same thing with this right-hand side, put the exponent out in front. So that's 2x plus 1 times log 3. Okay, and now if we're going to try to solve for x, we want to try to get all the x's on the same side. So first we're going to have to distribute this log of 3, which again, that's just going to be a number. I don't know what number that is, but when you have a number times 2x, you can multiply 2 with the number. So it's 2 log 3 of x, or not of x, times x, plus, and now we distribute log 3 to 1. So we get x log 4 equals 2 log 3 times x plus log 3 after we distribute here. And now what we can do is put everything that has an x on the same side. So I'll take x log 4 and I'll subtract 2 log 3 times x, and that's going to equal log 3. So all I've done is take the term that has x on the right, put it on the left, and now what we can do here, since both of these terms have an x in common, you can take out x, which leaves log of 4 minus 2 log 3 equal to log 3. So then we're almost done. To find x, you just take x times log 4 minus 2 log 3. We're going to divide whatever this number is on both sides. So log of 4 minus 2 log of 3. Take that, divide it on the left, divide it on the right. So now we get that this cancels, and we got x alone on the left, and that's going to equal log 3 over log 4 minus 2 log 3. This is the exact answer. And now to get the approximation, you're going to type in that into the calculator. So it's going to be log 3, and you're going to divide that all by log 4 minus 2 log 3. You get about negative 1.35. Okay, so that's the approximation. All right, just make sure that when you type this in on the calculator that you put parentheses around the numerator and parentheses around the denominator, and then you should be all right. Okay, so that's actually one of the hardest questions that you'll see when you're solving equations. All right, let's look at another example. Let's say we have the natural log of x minus 5 equal to 3. Well, there's a few different things going on. Remember that natural log is log base e, so if you want to write it like that, and I don't know why I keep switching from cursive L's to normal L's. Sorry about that. Maybe this helps. Okay, and actually, this isn't too bad. If we focus on this log on the outside, we see that there's a base of e, so there's not really much I can do except switch it to exponential form. Since the base is e, I could say that e, this base, to the third power, that's going to equal everything that's on the inside of that first log. So after we write it in exponential form once, we get rid of one of those natural logs, and now it's a little easier. But we're still kind of stuck. We really can't get x alone yet, so we're going to switch it another time. So one more time. Here's the base, so it's e, to this exponent. So now we put e cubed as an exponent, and that's going to equal x minus 5. And then to get our final answer, we can just add 5 to both sides. So x would be exactly e to the e cubed plus 5. And if you want to get an approximation, when you type it in the calculator, you do e to the e cubed, so this is one way to do it. Pretty large number. Okay? What is that? About 528491311.5. 52 million, nope. 528,491,311.5. Okay, and I mean, kind of makes sense. E cubed gets pretty large, and then that's 2.7 to a really big number. I mean, these kinds of problems, the answers generally are going to be pretty large. Okay? Let's keep it going. So we've done 2 different kinds of questions. I'm going to try to do as many different kinds of problems as possible so that you guys have a place to look in case you guys don't know what to do. All right, let's try this example. Let's say we have log base 10 of x squared minus 5 equals 4. So if we're trying to get x alone, I'm already stuck. What do we do when we're stuck? We switch it to exponential. So we're going to switch it. The base here is 10. The exponent is 4. And that's going to equal x squared minus 5. 10 to the 4, that's going to be 10,000 equals x squared minus 5. Add 5 to both sides. Oops. Add 5 to both sides. I didn't actually do that. There we go. Equals x squared. Now to get x alone, you square root both sides. So then x is going to be plus or minus square root of 10,005. Now, when you're solving log equations, remember that inside of the log, the argument can't be negative and it can't be 0. So when you solve, it's a good idea to kind of just double check real quick to see if that your answers make sense. And sure enough, when you square either one of these, you get 10,005, and certainly you can subtract 5 and you're going to be okay. If you were to plug one of these answers into this argument and you get a negative answer in here, then you would throw away the answer that gave you that negative inside the log. Okay, so you always got to be on the lookout for that. All right, let's try another one. Let's say 3 to the 2x minus 4 times 3 to the x minus 5 equals 0. All right, so this kind of has that feel like it might be quadratic, and it sort of looks like it. I mean, right here you see this exponent, 2x, is double this exponent, which is x. So a good idea is to actually do a substitution, and you're always going to take this middle base and power, and you're going to make that your letter of choice. I'm going to use u. So if we say u is 3 to the x, then when you rewrite this equation, 3 to the 2x becomes u squared minus, and now 4 times 3 to the x becomes 4u minus 5 equals 0. And look, now we have a quadratic equation that's fairly simple to solve. You factor, get your values for u. So u is going to be 5 or negative 1. But remember, this u represents a few different things. Okay? So now this is going to be 3 to the x equals 5. So there's one of the equations that you have to look at. And the other equation is 3 to the x equals negative 1. All we're doing here is replacing u with our original substitution that was 3 to the x. Okay? So now when we solve these equations, these are just regular exponential equations like we did in 5.3. Pretty simple to solve. To get x alone here, you can't really do anything except switch it. So it's log base 3 of 5 equals x. The exact answer we're going to change to base 10 or natural logs. It would be log 5 over log 3. So that's the exact. The approximate, if you type it in the calculator, log 5 divided by log 3, it's about 1.46. Okay, so that's one of the solutions here. And now if I take the second equation, if I try writing this in exponential, log base 3, if I try writing it in log form, log base 3 of negative 1 has to equal x. But right here we see that there's a negative inside of the log. We know that that's impossible, so we're going to ignore that case, and this would be the only solution right here. Okay? Let's see. Let's try another equation. Let's say log base 3 of x plus log base 3 of x minus 6 equals 3. Okay, so let me just compare this to something that we know how to do now. If you look at this example from earlier, we knew how to do this right away because we were stuck, but we were able to switch it to exponential. Looking at this equation, I can't really switch or do anything yet, but I can certainly make this left-hand side 1 log, just like we have in the first equation that we did with the log. So if you remember your properties from earlier, you can rewrite the left-hand side as 1 log. We're going to condense. When we're adding, you're just going to take the arguments and multiply them. So this becomes log base 3 of x times x minus 6 equals 3. Now is a good time to switch because there's not really anything else we can do to get x alone. So the base is 3. The exponent is also 3. And that's going to equal the argument, which is x times x minus 6. And now we solve this equation. So let's take a look. 27 is going to be x squared minus 6x. That's a quadratic, so we set it equal to 0. And again, we solve like usual. Factor, we get x minus 9x plus 3. So x is maybe 9 or negative 3. And I say maybe because, again, if this is a log equation, we want to go back, check to make sure that these values work. If I plug in 9, you can certainly do log base 3 of 9. If I plug in negative 3, you cannot do log base 3 of negative 9. Okay, so this answer right here we're going to ignore because it makes the arguments negative. X equals 9, though, is perfect. Alright, so that's kind of the idea. If you have an equation with a bunch of logs, make it into one log first, and then you should be okay. Alright, so that's the equations piece. Let's do a couple of inequalities. Those work a little different. Let's say I have 2 times 1.4 to the x, and let's say that that's less than 5. So here's an example. Alright, so if we're trying to get x alone, there's actually something I can do here, which is to divide by 2. So we're going to do 1.4 to the x is less than 5 over 2. Now we're stuck. However, we can't switch here. We cannot switch. And the reason we cannot switch is because this is an inequality, not an equation. Okay, so for inequalities, one of the things that you need to remember is that you can't just switch the format. Okay, because this less than or sometimes less than or equal to does not allow us to use that property or the definition of switching back and forth from exponential to logs. Okay, so now what we can do, though, we could go ahead and do a little trick, kind of like what we did in the very first example that we did. If we are not allowed to switch or it doesn't make sense to, let's just take the log of both sides. So if we take the log of 1.4 to the x, and then take the log of 5 over 2, now I can put the x in front just like we did earlier. So we get x times log of 1.4 is less than log of, and we know that that's 2.5. Okay. And now the last thing we're going to do is divide by log of 1.4. Okay. Now, I don't know about you guys, but I have no idea what this number is. Log of 1.4. Let's type it in the calculator just to see what it looks like. Log of 1.4 is 0.146. Okay. Now the reason I'm having you check that out, okay? Let's say that we were dividing by log of 0.4. Let's just say we're dividing by log of 0.4. If we're dividing by log of 0.4 as opposed to 1.4, you see that it's actually a negative number. So you have to be very careful because you have to remember that if you divide by a negative number, that the symbol actually switches. And sometimes it's hard to see that with logs if you have a negative that you're dividing by or a positive. So you always want to check here to see if you divided by a negative. If not, then you're good. Then x is going to be less than log of 2.5 over log of 1.4. And there's our exact answer for the inequality, and certainly you can type that in to get an approximation. Okay? Let's do maybe one or two more quick ones. Let's say we have log base 10 of x plus log base 10 of x minus 2 less than or equal to log base 10 of 24. Okay. Now, on the left-hand side, I don't want to see 2 logs, so let's make that into 1 by condensing. So this is log base 10 of, when you're multiplying, when you're adding, you multiply, so that'll be x squared minus 2x. That's less than or equal to log base 10 of 24. And again, because this is an inequality, we can't switch the format. Plus, I have 2 logs that are in the way. Okay, so a good tactic, the opposite of log base 10 would be to use the base of 10 on both sides. So what we're going to do is turn the left-hand side into an exponent, turn the right-hand side into an exponent, and now using the properties of logs, we know that if 10 to a power and log base 10 are inverses of one another, these cancel out and we just get x squared minus 2x on the left. Same thing here, now we get 24 on the right. When we solve this inequality, we set it to 0. It's another quadratic. We can factor and solve. We have to use key numbers because it's a quadratic inequality. You put those on a number line. So -4, 6. When you test your values, you're going to find that this is positive, so that's not going to work. If you maybe test -5. If you plug in 0 here, you get a negative answer. That's good in this case because we want this left-hand side to be negative. If you plug in something like 7 over here, you're going to get a positive, so that's going to be a no. This is less than or equal to, so this is where our answers are potentially. So right now, the solution is from -4 to 6. However, we want to check with the domains. We want to check with the original problem. Okay, so if we go back to the very first line here, there's no variable here, so we don't care. But we know that inside of a log, we can never have a negative or 0. So 1, we know that x has to be greater than 0 from this inequality, or from this first log. The second one we know is that x minus 2 has to be greater than 0, which means that x has to be greater than 2. So not only does x have to be greater than 0, it has to be greater than 2, and it also has to be between -4 and 6. So a good way to check what the final answer is going to be is to put all of these on a number line. So 0 is going to be here, open circle, shade to the right. X is greater than 2, open circle, shade to the right. And now the final answer that we got from the algebra was -4 to 6. So -4, close circle, and now we shade that one to the right. But we're going to stop at 6 with a closed circle. And now if you look at all 3 of these conditions, your answer is going to be where all of these intersect or overlap. So the final solution will be the numbers between 2. Since this is open, we need to keep this open. And then 6 looks like everything is closed here. So from 2 to 6. Okay? See you guys later.